In this video, we're going to be discussing the different chemical and physical properties, chemical and physical changes that matter can undergo, as well as discussing states of matter and state changes of matter. Again, you need either your notebook or the fill-in-the-blank notes and something to write with. Once you have all those ready, let's go. Okay, so we'll start off by talking about states of matter. Right, so our three different states of matter we're going to work with most commonly are solid, liquid, and gas. So we want to describe each of these in terms of their particle arrangement, kinetic energy, which is how much energy they have when they move, what type of motion they're allowed, the type of shape that they take on, the volume that they take on, how compressible they are, so how much we can smush them together even more, and how strongly attracted the particles are for each other. Okay, so if we look at a solid, in a solid, so our example of a solid on that right-hand side is ice. The particles in a solid are tightly packed together and they are rigid, right? So that ice is held into that hexagonal shape. It's a very rigid shape. Low kinetic energy. Ice particles do not move very much. In fact, the only motion that they're allowed, based on the fact that they're kind of locked into their position, is that they just vibrate in place. All solids have a defined shape. All solids have a defined volume. For most solids, you cannot compress them any more than they already are. They're as tightly packed in as you can get, and the attraction, or what we call the intermolecular forces, between different ice molecules are extremely strong. Right, so that means they are very attracted to each other. They're very hard to pull apart. In a liquid, the molecules are kind of close, right? Not as close as they are in a solid, but still fairly close. The fact that they're not as close together gives them a little bit more kinetic energy, so they can move a little bit more, which is why liquids flow. Liquids take the shape of their container, but they still have a defined volume, right? So if I take 100 milliliters of water in a beaker and I pour it into like a Dasani water bottle, its shape changes, but it's still the same 100 milliliters no matter what. Liquids generally can't be compressed very much, maybe a little bit, and the intermolecular forces between them are still kind of strong. Again, the particles are somewhat close together, so there's still a decently strong attraction between them. Then when we get into a gas containers or gas particles spread out as much as possible, right? They don't want to be near each other. That means since they're far apart, they have very high kinetic energy. Their motion, they move very rapidly. They have free motion between the particles. They take the shape and the volume of their container. Very easy to compress a gas, right? And even though there may be some small attractions as molecules move close to each other occasionally, for what's called an ideal gas, we assume that there are no attractions between the particles. We'll talk about this when we do gas laws later. The reason for that is it actually simplifies our math significantly. All right, so if you need to pause to finish reading on this chart, please do so. But for the sake of the voiceover, I'm actually just going to be moving on. Now, a property is something that you can observe or measure. Physical properties can be observed or measured without changing what the thing is, right? So mass, for example, is a physical property. I can put something on a balance and weigh it and get its mass without changing what it is. Same thing, I can measure the volume by pouring it into a graduated cylinder. Still the same thing, right? So all of these are things that you can do without changing the substance. A chemical property is something that you can only change, measure, or observe when the substance undergoes a chemical change, so when it reacts. The only way to know how flammable something is to set it on fire and watch. Right? Same with rate of reaction or heat. Heat of combustion is the heat generated when you burn something. Right? So that's something, again, chemical. You have to do the reaction in order to measure it. Again, if you need more time to write, feel free to pause. I'm just going to be moving on at this point. A physical change is something you can do to a substance and it still remains the same substance, right? So it's still the same thing, just might look a little different. So for example, if I take an iron bar and I saw through it, that's a physical change. I still have iron bar. I now have two of them instead of one of them, right? But it's still iron, it's still the same thing. Melting ice, it's still water. When in ice form, it's water. In liquid form, it's also water. Still the same thing. I haven't changed it at all. A chemical change is something you do to change the identity of a substance, right? So it turns into something different. Another name for a chemical change is a chemical reaction. So burning propane, for example. If I take propane, which is C3H8, it's a gas, it's what's used in the gas grills, and I burn it in oxygen, which is O2, I'll produce two compounds. I'll produce carbon dioxide and water, right? It's a combustion reaction. All combustion reactions produce CO2 and water as their products. So I start off with two reactants, propane and oxygen. I end up with two completely different products, carbon dioxide and water. Right? So that's a chemical change. The substances that are created are brand new. All right, so we'll go over some phase changes pretty quick. Now, endothermic means you have to add heat to get the reaction or get the change to happen. Exothermic means when the change happens, you get energy back or it's given off. Right, so our endothermic phase changes, we have melting, which is going from solid to liquid. Vaporizing, which is liquid to gas. Please notice I didn't say boiling. I didn't say evaporation. We'll talk about the difference later during the year. And if I want to go straight from solid to gas, that's called sublimation or sublimating. The exothermic phase changes. If I want to go from liquid to solid, it's not melting, it's freezing. If I want to go from gas to liquid, that's condensation or condensing. And if I want to go from gas to solid, that's called deposition. Right? So these are our 6 phase changes based on whether we have to add energy in or we get energy out. And for our, oh, by the way, all phase changes are physical changes, right? You are not changing what the substance is, just what it looks like at that moment. Now, for chemical changes, there are some signs of chemical change that you should be aware of, right? So, an easiest ways to tell that a chemical change has happened is if the color of an object changes. Color itself is a physical property, but changing color shows a chemical change happened. So, if a reaction started red and it wound up green, that's a chemical change. Whether you gain or lose heat, so whether the thing gets warmer or colder as the reaction progresses, is a sign of a chemical change. If you produce a precipitate, which is a solid, or if you produce a gas as part of a reaction, so the vinegar and baking soda reaction produces a lot of bubbles, CO2 gas, that's an example of a chemical change. Another example of a chemical change we'll get to a little bit later this year is if something produces light. Now, there are some changes where it may be hard to determine whether it's a chemical change or a physical change, right? So, for example, when you dissolve something in water, well, it's physical because you're changing what it looks like, but it's still the substance dissolved in water. But it could also be chemical because you're breaking bonds and creating new things. That's kind of hard to do. Look at it on a case-by-case basis. And a good example is, what happens if I undo the change? If I get my thing back, it's probably physical. All right, so that's it for changes and properties of matter. In our next video, which is the last one for Chapter 2, we'll be talking about how to separate mixtures into their individual components.